Our task now is to use this approximation for the second derivative of a function to crudely solve du by dt is d squared u dx squared. This is the heat partial differential equation. On the domain x is between 0 and 1, and such that the boundary value of u at x is 0 is some constant a, and the boundary value of u at x is equal to 1 is some constant b. So first, let's draw a diagram so we can define some variables. Here's the x-axis. We're interested in the domain 0 to 1 because that's where the heat PDE is defined. And what we're going to do is be very crude. So we're going to introduce one point in the middle, that's a half, and we'll give these names x1, x2 and x3 with 0, half and 1. Now what we're going to ask is what is the value of the field u at this point x2, right? And let's define that u2 of t, so whatever u is at this point as time varies, is u of a half t. Now, let's have a look at the differential equation. Du2 dt, how this changes in times, is the partial derivative of this, du by dt, evaluated at a half t. But from the differential equation, this time derivative has to be the second space derivative. So that's equal to uxx evaluated at a half t. But now we've got a formula for the second derivative, an approximation, and that's this. And so the question is, what value of h can we use? And the answer is, let's use h is equal to half, so that when we go f of u of x plus h, that's u of x plus a half, and we'll go from a half to 1. And similarly back here. Alright, so the formula says u of xx is approximately 1 over h squared, so that's 1 over a half squared, times u at a half plus h, that's a half, minus 2 u at a half t, plus u of a half minus a half t. Okay, now we can do things with this, because 1 over a half squared, that's 4. U of a half plus a half t, that's u of 1t. U of 1t is the boundary value b, because this approximation is looking at distance h over here and finding the boundary value. Minus 2 u of a half t. U of a half t we've called u2 up here, and then plus u of a half minus a half, that's u of 0t, and u of 0t by the boundary value, or boundary condition on the left, is a. So what we've got now is that du2 dt, I've left out that 2, is approximately 4 into a plus b minus 8u2, i.e. du2 dt is plus 8u2 is approximately 4 into a plus b. Right, now the nice thing about this is that it is a linear first order differential equation, and you will have solved this in a wide variety of differential equation courses. So with a little bit of work from one of those courses, we can find what the solution is, and I'll leave that to you. Here we just write down a general solution. So the general solution is a plus b over 2 forced by this term, plus some arbitrary constant, say C1, e to the minus 8t. Right, and that's our crude prediction for what goes on at this midpoint, x is equal to half, as time varies. Namely, there's an exponentially decaying transient, and then the solution tends to the average value of u at the left and the right. And this is quite a reasonable thing for it to do, because this is a diffusion equation, and in diffusion equations things just smooth out. Question is, what's this arbitrary constant c? C1 is determined by the initial value of u at this point, and hence it's determined by an initial condition, which I have not specified up here. But once an initial condition is specified, C1 is found, and this then becomes the solution, the crude solution.